Hello everyone, my name is Andrzej Dereszowski, and this talk will be about FunCap, which is an IDA Pro plugin or script to make static analysis faster by combining it with some runtime debug information coming from a debugger. So a few words about me. I'm a freelance security consultant with focus on incident handling, forensics, and malware analysis. I'm not a dedicated reverser. Reversing is just a part of a larger process that I apply to analyzing malware, and as such, I avoid this reversing process as much as possible because it's just too time consuming. It takes too much time. So this is basically the reason that I decided to write FunCap, because to speed up reverse engineering. And the problem that I had is that the tools that an average reverser like me uses are mainly IDA Pro and OLI-debug. There are some tools that are used by real reversing gurus like PIN, MetaSem, Vivisec, and so on. But these tools are out of scope for this presentation, for me, and from other average reversers that are not the real gurus. And this is the presentation is addressed to them, to those people. So, and yeah, here is the problem. OLI-debug gives a lot of good info during the debugging session, like this information here about arguments, but they are not visible in IDA. Later on, when we try to combine this debugging session and with the static reversing with IDA, we won't see this. We would have to keep the debugger open and or manually move this kind of information, but there is no automated way to do that. Also, another problem that stems from the same issue is that when there is an obfuscated code that we were able to get to using OLI-debug, there is no easy way to move that code to IDA and to start analyzing it, because you have to rebuild the executable to be able to load it in IDA, which is sometimes challenging because there might be sometimes you need to rebuild the PE header, but it's the simplest part, because sometimes there are import address tables that are obfuscated and so on. So again, it requires time. And in short, the problem is that there is no automatic connection between these two tools. So I had this idea to connect both worlds and provide an automated solution to have these two sort of information in one place. So historically, first I wanted to use IDA Pro Tracer, but I realized that it's too slow and it's not generating the right info that I need. The final inspiration that I liked the most, the solution that I liked the most was Paymain Stalker written by Pedram Amini, which is bundled with PyDebug, which is an old and not developed anymore toolkit to analyze to debug scriptable debugger in Python for Win32 userland. And Paymain Stalker had that very simple idea of placing breakpoints at each function, at the start of each function, at the end of each function, on imported IDB. So it used to take the IDB to have the executable broken into functions, and then was placing these breakpoints on each function start and end, and then it was capturing some context information. It was running the executable, capturing some context information based on that breakpoints, and was generating an IDC script to export back that data into IDA Pro. But it had a lot of limitations. It was old, not developed anymore, only Win32, and yeah. So I finally decided to implement this solution by using IDA debugger. It's pretty good debugger. It has a lot of connectors to a lot of platforms and a lot of operating systems. So that was my idea. And let me introduce FunCap now. So like I said, it's an IDA Python script plugin. It aims to combine runtime info and feeds into the static listing. And the best example is here on that picture. So you can run some code into the VM under the control of IDA debugger, and the script will automatically paste some kind of useful information like this. So for example, on this picture you see the argument 0 captured, which looks like junk, and then it was dereferenced again after the function call, and it contains some readable URL, which means you don't need to really analyze that function to know that it's decoding some strings. So the result of this is that you understand some functions without even looking at them. Just like I said, it saves a lot of time. So how it works? It works very similar to PayMe. It places breakpoint on function call instructions. That's the change I made. You can still do like PayMe did, placing breakpoints on function starter end, which makes the listing in IDA look better, but I recommend the calls because you get more information when you place breakpoints on calls. You can catch multiple calls from different places of code to the same function. It then runs IDA debugger after placing these breakpoints. When the breakpoint is hit, it tries to dereference contextual information. So these will be arguments. It tries to guess how many arguments the function has by using IDA analysis, and it tries to dereference some arguments that might be valid pointers. It tries to guess if it's a pointer, if it's a valid address, if it's a string. It performs some guessing, and it captures that information. Then it places breakpoint after the call, the call instruction to be able to capture the same context again, and they reference the same pointers and see how they changed. This information is then dumped to a text file and is inserted into the IDA listing. And yeah, this is a very simple idea indeed, but it kind of works. So let me now mention some features that you can use FunCap for. So the supported platforms, I tried to develop FunCap to be as generic as possible. So it has a generic classes, and then you can inherit and implement platform and OS specific classes. And for now, it's easy extendable, but for now it supports IA32, IA64, and ARM thumb as hardware platforms. It supports Win32, Win64, Linux 32, Linux 64, Android. As for operating systems, there is no Mac OS support yet. I haven't tested it neither on Mac OS nor on iOS. It supports almost any IDA debugger connector. I tested most of them. Even pin tracer connector is going to work. Another feature is that it builds a runtime call graph, which is of course very different than the static call graph that IDA generates, because you will see on all these indirect function calls too. It has a code discovery mode to automatically deal with packers. I will show a demo of that. It basically tries to detect if the call leads to a code section that was not seen before, and then if yes, then it will analyze that segment and it will discover it as such. It also resolves indirect function calls, as you see on this example. Call to dword here is commented out as call to an API. Yes, of course, the API calls can be captured as well. The full context is dumped to the file, and only the subset of this context is pasted into the IDA listing, which is made to make the listing still readable. If we were to paste the full context, it would be completely messed up. You can configure FunCap to also capture hex dump, hexadecimal data instead of ASCII. ASCII is the default one, like the first picture, and the hex dump you can see on the second one in the bottom. It implements recursive argument dereferencing. This is an idea taken from PIDA for GDB. And as you can see, after calling this get main args function, some arguments, some pointers in arguments are followed multiple times, and finally they are resolved into strings. The capture scope is easily configurable. You can select which registers to capture. Some of them are selected automatically based on the analysis of the function. You can have a recursive function hooking mode for large binaries. So a frequent question that I'm asked is that if there is a lot of functions and you place breakpoints on all of them, and if it's a large binary, then it will be very slow. Yes, that's true, and for that you can use the recursive hooking, when you can basically hook the win main or the first function that is called, and from there FunCap will hook recursively as it goes. It has only a command line interface. There is no GUI interface. And also another feature that it provides is that the functions that were called are actually marked by a different color, which is an easy way to see which functions were called. So let me now show you a little demo. I will show you a few examples, and I will start with some basic example, and then move on to some more advanced ones. So the first example that I would like to show is a TIDOR backdoor that was used extensively in targeted attacks a while ago. So we can see that it's a very simple backdoor, only a handful of functions here. We first select a debugger. Here it's a remote Windows debugger, that's okay. We load FunCap, and we hook the segment, the current segment, and then we are ready to start. Yes, it will load. It will transfer the executable to the virtual machine, and you can see that it's capturing some information. We can straight away revert the virtual machine for the next example, and here you can see that there are some functions marked on a different color. Those were called, and you can see that we have some information pasted here. For example, here this function was called with some junk argument here, and when it was dereferenced again, you can see that this is a URL of the command and control server, which makes it unnecessary to analyze this function. Of course, it is a very simple function, but it doesn't matter for FunCap. If it was more a complicated encryption function, it would also be good for us. Here you can see that FunCap captured a registry key name. This is also a very simple encoding, and you can see, as you can see, but that again doesn't matter. Okay, that was easy. Let me now load a next example. This would be a file that was used some time ago, also by targeted attack. It also has a small number of functions, but as you will see, there is a obfuscated code that will be detected by FunCap. So let's do the same. So we select remote Windows debugger, and in this case we have to, because it's a DLL, so we have to fill in some options here so that it can be started. That's okay. We can load FunCap now again, and this time we use the code discovery mode, and we use no jumps to make it a little bit faster. We can hook the segment now, and we can hopefully run it. Okay. Okay, so it runs and it captures some arguments of function calls now. So it turns out that there is a lot more functions that were displayed. We can already see that. Okay, that currently we can pause the process already, and first I would like to show you in that on the console. Let me just find something. Here, as you can see, FunCap has detected some new code section. As you can see, this call is calling to a function that is located in another segment, 9C299. And if you now have a look at a function list, indeed, there is a whole new segment of functions that has been detected. And these functions were also traced by FunCap. As you will see on the example, we have some strange domain names here captured, and these probably are domains where this malware will connect, that we can already guess this out. There is some also an argument of a local computer name, which makes us think that it's going to be used somewhere. Here you can see that the call to dword was automatically commented as a call to internet get connect state, and here you see some HTTP request that is being built. So automatically we don't need to rebuild this PE, and we can start analyzing it right away from here, from IDA Pro. So now I will move to the next example. So we revert that, and I will open a new example. So this sample is a sample of a Z-bot Citadel, and this malware has interesting obfuscation routines here, that basically these are all junk instruction and also a junk function calls, as you can see. So let me again start the debugger and load FunCap. So I will enable code discovery again, and I will hook the segment, and we can start the process. Yes, yes. Now we don't need to analyze. And now I would like to show you how I used the graph, the call graph, runtime call graph in FunCap to actually see what's going on. So, okay, that we can stop here and we can see the functions again. We have a new segment also which starts with 38 here, and I can show you on the graph. So this is the runtime graph, and here you can see that there is a lot of function calls like that, and finally it moves to a new segment. So we can figure out that all these here, these are junk function calls, and the real processing of this malware, it starts here. Okay, and that's all the live examples that I wanted to show. One other example that I would like to show you is when I was using this FunCap for the analysis of Ouroboros rootkit, also known as Snake or Turla. Here it was a kernel mode code that I was running with FunCap, and on this example here you can see that when Ouroboros is processing its Q file, and which is the configuration file of Ouroboros, and is getting some information to inject into user mode process. Another example would be where the name of the one of the named pipes Ouroboros uses to communicate is getting automatically resolved by FunCap. Another example would be something from the ARM architecture. Here I was running an Android emulator, and I was hooking SH process, and I was trying to do some rubbish instructions, but those instructions were successfully captured by FunCap as well, as you can see. Okay, that's all the examples that I wanted to present. So what are the limitations of FunCap? It will not follow newly created threads in recursive mode. So when you're using recursive threads, watch out, it will not breakpoint on create remote threads thread and will not do that. Code injected to another process is not going to be followed. Yes, if there is a code injection, you also have to know that FunCap will not follow this injected code. The call graph is a bit unfriendly. It's not actually a bit unfriendly, so it's really unfriendly, and you cannot search and stuff like that. Only basic types are dereferenced, so there is no structure dereferencing, and so there's strings, int, pointers, and that's it. And the argument count determination is not yet very accurate on IA64 and ARM architectures. So Now, what are the future directions? The thread following that I just mentioned, this can be, I think, easily resolved by breakpoints on thread creations, or a given API for in an operating system, such as create remote thread or create thread and stuff like that. The remote process code injection following that was just mentioned, I was also thinking about this, and what I was thinking about is to create a Cuckoo plugin that can trace injected code, and just, you know, like dumping the new, you know, like creating new IDBs for each injected code and dumping it as and giving it back in a package generated by Cuckoo. Or you can also switch to entirely to kernel mode debugger, and then you can trace the code that is injected, but it's not that easy. Better graph solution. Well, currently in IDA there is not much to be done by a script to make a better graph, so I was thinking about going to some external application like Gephi. Better argument count determination and complex type support. This is I'm planning to do that anytime soon when I have time. Not the complex type support, but the argument determination on IA64, and actually on all the architectures, to automate that and to better determine which register are used to pass arguments to functions. There was also an idea in my head some time ago to use the decompiler plugin to guess types and to capture, you know, to custom those guess types. But again, this is not so easy. I also was thinking about doing some database and automate it a little bit, so that you can have multiple passes of the same code, and you can switch them from IDA GUI, so that you can see, you know, like multiple calls from the same address with different arguments and stuff like that. But again, that's a lot of work. So that's basically it. If you have any questions, do not hesitate to mail me or create issues on project's GitHub page. Thank you very much.